Catch the way, everybody. So just now we have done with potential energy and potential energy of a system of charge. So now what I'm going to do is potential energy of a charge in external electric fields. External electric fields. Potential energy of a charge in external fields. External field, let's say E. This is what we are going to do now. So what I'm going to do here is, let me draw an electric field. Let's say this is electric field. I have electric field like this. This is electric field. This is electric fields. And now when I have an electric fields, every point in the electric field has some potentials. Alright. Every point in the electric field has some potential, and the potential vary along electric fields. Potential doesn't vary perpendicular to electric fields. Potential doesn't vary perpendicular to electric field. Potential vary along electric fields. So therefore, I can choose any point in a electric field and then assign potentials. So let's say this is R1. I choose a point, let's say R1. So I can define the potentials. Alright, let's say V1 is external potential. V1 is external potential. V1 is potential at R1. I can call it as external potentials. That is potential due to external electric field. Potential due to external. And this can be defined as amount of work required to bring a unit charge from infinity to that point. Amount of work required to bring a charge from infinity to that point is what we define as potential at R1. So I assigned potential V1 at R1. This is external potentials. Alright. So now what I'm going to do is if I bring Q1, let's say if I bring a Q1. If I bring a Q1 at R1, how much work is required? When there is no electric field, then no work is required to bring a charge Q1 from infinity to point R1. Why? Because there is no electric field. Right? Q1 can come freely. Alright. Now, unlike without field, with field, now Q1 has to go against external electric field E. Alright. Q1 has to bring we have to bring a Q1 against external electric fields, right? So now I say, let's say W1 work required to bring Q1 from infinity to R1 against vector, right? Against external fields is given by, look at here, this can be given by, this is equal to Q1 V1. What is V1? V1 is a potential at R1. This is potential at R1. This is potential at R1. Alright. And I can choose another point. Let's say R2. This is R2. Now I can assign potential at R2, right? Potential at R2, I say external potential at R2 would be, let's say, V2 R2. Okay, now V1 is different from V2. Alright, V1 is different from V2. Now, how much work is required to bring Q2 from infinity to R2? Is work is equal to work required to bring Q2 from infinity to R2 would be Q2, let's say, I write against external field, against external field, E would be equal to Q2. This is, and again, when I bring the Q2 and give it at here, one has to do work against Q1 also, right? Alright, this is V2, then V12 would be work required to bring Q2 from infinity to R against, this is the difference, right? Against Q1 is given by Q1, Q2 divided by 4 pi epsilon naught R12. This is what I have. This is R12. So, how much work is required to assemble Q1 and Q2 in external electric field, right? Total work. Assemble Q1 and Q2 at R1 and R2 is equal to Q1 V1 plus Q2 V2 plus Q1 Q2 divided by 4 pi epsilon naught R12. This is the point. So V1 is a external potential at R1, V2 is the external potential at R2, and this is interactions between Q1 and Q2, and this is interaction with between a Q1 and the external electric field at point 1, and this is interaction between a Q2 and external field. This is what I have, and this is the total work, and the total potential energy. Finally, I write total potential energy is total potential energy stored would be total potential energy stored is equal to Q1 V1 plus Q2 V2 plus Q1 Q2 divided by 4 pi epsilon naught. This is the point. Alright, this is for two church, right? Then I can go on for 3 church system, 4 church systems, go on like that. So you can do like as a homework also, right? So this is what we talk about potential energy of church in external field. 1 church in external field, 2 church in external field, number of church in n number of church in external field. You can derive it, right? All right, now what I'm going to do is dipole. All right, potential energy. All right. So if I put a dipole in the external electric field, then how much work is required, and what is the potential energy associated with a dipole with some orientation, right? With a certain orientation of a dipole in an external electric field. So next is dipole, right? So first what I'm going to do is, what happens if I put a dipole in an external electric field, right? This is what exactly is going to happen, right? I have a dipole, and what happens is this is the positive charge. So the positive charge tend to move along the electric field, and negative charge tend to move opposite to electric field. All right. So therefore, what happens is that you can hear a dipole in an external field there is a uniform external fields. There is a uniform external fields. Now what happens is that net force is going to be, I just say, comes dipole of dipole moments. All right, dipole of a dipole moment P. Right. So what I mean is that this is a force on the electric positive charge. Positive charge tend to move along external electric field, and negative charge tend to move in the opposite direction of the electric field. And what about net force? Net force is going to be 0. Net force is 0. Why? Because this goes that side. This goes in this opposite directions. This along my, so the total force is equal in opposite. Therefore, net force is 0. However, it has net torque. This is what we have done in the first chapters. Why? Because forces are acting along, not acting along the axis. Forces are acting parallel to each other, so therefore it has net torque. And how much is torque? This is the torque. This is the torque. Torque experienced by, this is the torque experienced by a dipole in an external electric field. Right? So this is the torque. And this can be represented, the magnitude of torque is given like this. This is the magnitude of torque. Now it has torque. And we talk about the torque is determined by, the amount of torque is determined by the angle, right? That is angle between dipole moment. This is the dipole moment angle, right? This is dipole moments. The direction of dipole moment is always from negative to positives. Alright. This is what I have, right? Now, what I'm going to do is potential energy by a dipole in external electric field. So we have two methods to find the potential. I will do both. So first, what I'm going to do is I will try to rotate it, and how much work is required to rotate a dipole, and that work is stored as a potential energy. And second one is what I'm going to do is how much work is required to assemble positive Q and negative Q in a external electric field, and that work is stored as potential. So these are the two methods. So first method I'm going to do is rotate, right? So this is the torque. So what I'm going to do is let's first I say apply the external torque and rotate the dipole to a very small angle, right? Right? Let us rotate dipole, alright, in an external field, in an external fields. So small angles, let's say delta theta. I just rotate a dipole to a very small angle, and then amount of work, right? Amount of work is given by, this is what we have done, right? This is what we have done in class 11, right? If you remember, right? This is amount of work, very small amount of work. Now what I'm going to do is, this can be written as, okay, now I'm going to rotate, total amount of work required to rotate, total work required to rotate dipole from theta 1 to theta 2 would be I'm going to rotate from theta 1 to theta 2, right? This is the what I'm going to do, and then this would be I'll integrate it. First I found for a small angle, and then once I found a small angle, I will integrate it. And when I integrate, all right. So I'll do integration. What is integration of sine? It's minus cos theta, right? So integration of sine is minus cos theta. So total work is equal to PE minus cos theta. Limit is from theta 1 to theta 2. So therefore this goes like PE cos theta 2 minus theta 1. This is the total work. This is the total work. And what I am going to choose is, let's say, I'm sorry, this is cos theta 1. Cos theta 1 final minus initial. Alright, so this can be written as minus PE plus PE minus PE cos theta 2 plus PE cos theta 1. Now once if I put a limit like, let's say theta naught is equal to, let's say theta 2 is equal to theta, and theta 1 is equal to pi by 2. I rotate from pi by 2 to some theta, then work is equal to cos theta. And why? Because cos theta by, I'll write this step once more. Alright, so this is going to be 0, and this is the final expressions. This is the final expressions. Alright, and now this can be rewritten like this is a work, and work is stored as a potential energy. This work is stored as a potential energy. Therefore, this can be written like PE Alright, this is what I have. This is the final expressions. So what is the potential energy stored by a dipole in accelerated field is this. Alright, so this is the final expressions. P dot minus P dot E. This is the one way of finding out, that is by rotations. Now second method I'm going to apply is, I will assemble, right? How much work is required to assemble? Q1 and Q2. So I'll write here the final expressions. Potential is equal to minus P dot, this can be written like minus PE cos theta. Okay. Yeah. Now I'll use the second method to bring or to assemble Q1 and plus Q and minus Q in an external electric field. Alright. Both are one and the same. Alright. So this is potential 2, this is potential 1. Okay. So work required to bring plus Q at R1 would be equal to Q1 V1. Okay, and work required to bring minus Q at R2 will be equal to minus Q V2. Alright, this is the point. And then interaction between the Q1 and Q2, alright, work for Q1, Q against minus Q is going to be minus Q1 Q2 divided by 4 pi epsilon naught 2a. Why 2a? 2a is a distance between 2a is distance between two charges. Now what about total work now? Total work is equal to Q1 minus Q V1 QV2 minus Q1 Q2 divided by 4 pi epsilon naught to A. Now I take formula. Alright, now what is Q1 minus Q2? I write here Q1 minus Q2 is Q1 is a smaller potential and Q2 is a higher potential, right? We have done that. Potential decreases along electric field and potential increases in opposite direction of electric field, right? And we say that relationship between the potential difference and the electric field is such that, look at here. What is the perpendicular distance? This is the perpendicular distance. A cos theta plus A cos theta, right? So this is going to be A cos theta, 2A cos theta. 2A cos theta is a perpendicular distance between two potentials. I can create here one potential surface. I can create here another potential surface. What is the normal distance between the two potential surfaces? Normal distance is going to be this. And how much is this? This is equal to 2A cos theta. Alright. And then I'm going to put electric field E. Then I'm going to put electric field E. Alright. So having this, so this change in potential would be equal to, I'm going to put here minus. Why? Because Q2 is greater than Q1. Alright. Therefore it is minus 2A cos theta E. Alright. So I'll bring here minus, I'll keep this, and 2A cos theta E, and then minus Q1 Q2 divided by 4 pi epsilon naught to A. What is 2AQ? 2AQ is the P. This is P, right? So this is equal to minus P E cos theta Q1 Q2 divided by 4 pi epsilon naught to cos theta. And I say this is going to be very small. This is going to be very small. So why? Because the electric field is so strong that the interaction between the Q1 and Q2 is almost negligible, right? So therefore total work can be written as minus PE cos theta, and work is stored as a potential energy or else this is written like minus P dot. So expressions are one and the same. Expressions are one and the same, right? So these are the two methods. You can choose any of these and then write an exam, right? So this now what I'm going to do is few case, right? That is now if I keep a electric field, right? Case number one is that if a dipole moment is along electric field, that is theta is equal to 0. If theta is 0, then cos 0 is 1, then potential is equal to, if potential energy stored is PE, and this is negative potential. So negative potential energy, and that means energy is minimum. Energy is minimum. Energy is minimum. If energy is minimum, then dipole is stable, right? The dipole in the state of dipole is stable, right? Stable means minimum energy. Now, if I say second one, if P is opposite to E, then theta is going to be 180 degree, and cos 180 is equal to minus 1. So therefore, U is going to be minus into minus is plus, PE, here plus, and then positive potential energy. So energy is maximum, right? Maximum energy. If energy is maximum, then state is unstable, right? Unstable state. This is unstable state. Now, if P is perpendicular to electric field, theta is 90 degree, then cos 90 degree is equal to 0. So potential energy is 0, and we call it as a mean positions, right? Mean positions. Mean position is a position where potential is said to be 0. So these are the 3 different cases. Alright. So very important for examination. Alright. Now what I am going to do is electrostatic conductors. A very important properties of electrostatic conductor. Alright, so electrostatics of conductors. Alright, so under electrostatic conductors, right, if a conductor is under electrostatic, alright, if conductor is under electrostatics, right, so what is electrostatics? So this is what first of all I'm going to define this, and then all the property can be explained easily, right? So when I say electrostatic, this is very important, right? When I say electrostatics, that means flow of charge is 0. Charge is 0. That means no flow of charge is taking. No flow of charge is taking. No flow of charge is taking place in conductor. Taking place in conductor. In a conductor. This is very important, right? When I say electrostatics, there's no flow of charges taking place in a conductor. That you should keep in mind. So whenever we talk about electrostatics of conductor, there's no flow of charge. Alright, the conductor is electric charge in a conductor. Free charge in the conductors are at rest. Free charge in the conductors are rest. Alright, so this is what I have. And having this, I'll explain all the points. So the first point I would like to discuss is inside the conductors. So the point here, main point is, you should not, you should create a condition such that there is no flow of charge taking. If a flow of charge is taking place, then this contradicts the electrostatics of conductor. So you are not supposed to let charge to flow in conductors. So under such a situation, what is that situations? No charge, no flow of charge is taking place. Under such situations, number 1 is inside the conductor, electrostatic field is 0. Inside the conductors. Inside the conductor, electric field is 0. This is electric field is always 0. This electric field is always 0 inside the conductor if conductor is electrostatic. If conductor is electrostatic, right? So now let's say if it's non-zero, let's say if this is non-zero, then we will see. If this is non-zero, then there will be some electric field. If there is some electric field, then the free charge will move. Alright, if this is non-zero, then flow of charge take place, which is not possible, right? Which is not possible in electrostatics. So now, if I take a non-zero electric field inside a conductor, which is not possible, right? If a non-zero electric field inside conductor is not possible, then what is going to be a possible, right? Alright, then zero electric field in a conductor is possible. Alright, I just contradict and then prove it. What I contradict is contradict the fundamental property of electrostatic conductors. If I choose a non-zero electric field in a conductor, then this opposes the fundamental property of electrostatics. So therefore field is zero inside conductors. Field is zero inside conductors. So this is not possible. Field must be zero inside conductors. So this is how I proved. Now second is that at the surface of charged conductor, electrostatic field must be normal to the surface at every point. Now the second point I am going to prove you is, again I say that I have a surface. Let's say I choose a surface. This is a surface. I have, this is a charged surface. So now if I say that if a charge is not normal, right? If a charge is not normal, right? This electric field is not normal to the surface. If electric field is not normal, normal means perpendicular or perpendicular to the surface. If electric field is not normal to the surface, then field component along surface is non-zero. Then this we can obviously say that field component along a surface is non-zero. If a field component along a surface is non-zero, then there is a flow of a charge taking place on a surface. Then flow of charge is possible on the surface, which is not true. Alright, which is not true, which opposes the fundamental behavior of electrostatic conductors. So therefore, if this is not true, if an electric field is not normal, if an electric field is not normal to the surface, is not true or not possible, then what is going to be? Then electric field must be normal to the surface. If electric field is normal to the surface, then field components along surface is zero. Field component along a surface is zero, and that is why no flow of charge along surface is possible. So which is very electrostatic. Alright. Now next point number 3 is interior. The interior of a conductor can have no excess charge in the static situations. That means that they mention like in the static situations. Alright. There is no possible, right? Alright. You can't create excess charge inside conductor under a static situations. Why? If you ask why, let's say I have a conductor and I create some positive charge. If I create some positive charge, and this positive charge will create a non-zero electric field inside the conductor, and this non-zero electric field will let the charge to flow, which is not possible. Very simple, right? So if there is an excess of charge is possible. Now every time I just take the opposite of this, I contradict and then prove it, right? When I have an excess number of charge, then electric field is non-zero inside electric field, which is not true. Why it is not true? Then there will be a flow of charge. Alright, so point number 3 is done. Now point number 4 is electrostatic potential is constant throughout the surface, constant throughout the volume of conductor, and has the same value as inside or on the surface. So that means in the volumes, alright, potential is going to be this. So potential inside is equal to potential on the surface. Again, the reason is that if there is some potential difference between inside and the surface, again there is a flow is possible, right? So if I have a spherical shell, charged spherical shells, if I have a charged spherical shells, we know that electric field is zero. This is what we have done in first chapter. If electric field is zero, then potential is constant. Now answer is how much potential? Potential is equal to, this potential is equal to potential on the surface. This potential is equal to potential on the surface. So potential on the surface and potential inside volumes are same. So under which electrostatic is possible, right? Electrostatic conductor is possible, right? Now fifth point is electric field at the charged surface of conductor is given by this. I have here, this is what I have, right? So I choose this, I take a Gaussian surface, this is the Gaussian surface, cylindrical Gaussian surface. What is the total flux? Total flux through this Gaussian surface is going to be, flux is going to be enclosed charge using a Gauss's law. This is Gauss's law. Let's say a Gauss's law. Alright, which is equal to sigma A divided by epsilon naught. Alright, now next is again flux. What about electric flux? Electric flux is equal to electric flux EA. Why? Because there is no electric field crossing this, so therefore we don't need to we write only this flux, and this flux is equal to other flux. So AA cancel out. And what about charge? Electric field. Electric field must be equal to this. So this is electric field, or this is actually I've done it in the first chapter also. This is electric field, and I'm going to put vector signs. N cap is a unit vector. Why? Because it is outward. So this is N cap is this is, let's say this is sigma is for positive charge. If a sigma is for negative charge, this is going to be a minus. This is minus, sigma is negative. Inward and outward. This is electric field at the charge at the surface of charge conductor. Now last is electrostatic shieldings. Now this is the applications or implication of all the 5 properties, and all the 5 property talks about under electrostatic situations, under an electrostatic conductor. In an electrostatic conductor, electric field inside conductor is 0. Since the electric field inside conductor is 0, no matter how strong electric field is outside conductors, so therefore it acts as a shielding. It shields against external electric field, right? So says that electrostatic shielding is that whatever be the charge and the field configuration outside, any cavity in a conductor remains shielded from outside electric influence. So this is all huge applications, right? So when a lightning strikes on you, if you are sitting in a conductors and you won't get any damage, right? So this is the point. So this is the electrostatic shielding, right? So electric field inside conductor is 0. Alright, electric field conductor is 0. So therefore, no matter you see so many charge, but however electric field inside conductor is 0, right? So if you have an electric field, this is electric field, but then electric field almost remains 0. So therefore, you cannot be affected by external electric field as long as you are inside conductors. So this is what I have. So V is inside this spherical whatever, right? metals, and then electric field is always zero. And if you put this in the earthing, then whatever charge goes inside this, goes into earth, right? So with this, I have come to an end of electric potential and potential energy and property of electrostatic conductor. Thank you.